Okay, using inverse variation, we want to be able to recognize and use inverse variation. And of course, use joint and other variations. And before we go into inverse variations, back in Chapter 2, we did cover direct variation, and what that dealt with is y equals kx, and k was my constant of variation. And what we learned here, when direct variation, basically as y increases, x increases by some factor of k, or if y decreases, x decreases by that same factor of k, or by a different factor of k. So those two things worked together. What we're going to find out with inverse variation, and it can be written as y equals k over x, or if you did a little bit of inverse operations, we would have y times x equals k. And that just means as one of these increases, the other one decreases, or vice versa. As one increases, the other one decreases. So as y gets larger, x would have to get smaller, or as y gets smaller, x would have to get larger. So that is the inverse variation. And that may seem a little bit confusing now, but as we start to use it some, it will be a little bit more clear. So looking here as inverse variation, let me go ahead and get these tables in here real quick. Okay, so when trying to find out how does this relationship vary, directly, inversely, or neither, sometimes I may accidentally say indirectly, but what I mean is inversely. So if it varies directly, well, we know that directly is going to be y over x, as we this would also equal y over x equals k, if you just reworded or reordered that formula using so as we look at this, I have 8 over 0.2. Then I have 20 over 0.5, and then I have 40 over 1, 60 over 1.5, and it looks like each one of these is going to be 40, 40, 40. So it turns out that k, my constant of variation, it seems like everything is changing directly, because I've already used the directly. I didn't even get a chance to go over here and say indirectly what's going on. If it works directly, then we know that it is k equals 40, and then I have y equals kx, so y equals 40x, and it is, again, direct. And just to prove that it's not inverse, I know that if I have 0.2 times 8, I get 1.6, and if I have 20 times 0.5, I get 10. So obviously that's not working. So there we go. We have our first problem. It's direct. We found out the constant variation was 40 because that's what it was changing by. And then we substituted 40 back into the formula to get the model that we were looking for, where it talks about write the model for the direct and inverse variations. So again, over here, if we take B and we have the direct variation, so if I have 40 divided by 0.2 is going to be, going to have to do the math one on that one, but I know that 16 divided by 0.5 is going to be 32. And I know that 40 divided by 0.2 is not 32, so if it's not constant, then it's not direct. But if I take over here and I have the indirect, which is x times y equals k, I get 0.2 times 40 is 8. I get 0.5 times 16 is 8. And I get 1 times 8 is 8. And 2 times 4 is 8. So it looks like k is equal to 8. So if k is equal to 8 and all of them are now inverse, so I have y equals 8 over x, because if you remember, the formula was y equals k over x. So indirectly, there we go. My constant of variation is 8, and then y equals 8 over x is the model for that. And this last one, let's see here, I have 40 divided by 0.5, which is going to equal 80. I have 12 divided by 1.2, which is, gosh, I think that's 10. Either way, I know it's not 80. And over here, if I have x times y, I have 40 times 0.5 is going to give me 20, and then 12 times 1.2 is going to give me, I think, 14 times 4, but either way, this is neither. It is neither direct, it's not direct or indirect. So it is neither. There you go. So that's how we were looking for that direct and inverse variation. Determining an inverse variation. Well, let's look at what it's given us. We know that inverse variation can be written x times y equals k, and suppose that x and y vary inversely, so there's inverse, and x is 8, so let's just substitute in x for 8. Y is going to be 7, and that is going to be k is going to be equal to 56. So it says, what is the model here of inverse variation? Well, y equals k over x, or we replace k, y equals 56 over x. There's our model. And it says, what does that graph of this look like? Well, without getting too particular, I know that if I plug in some values for x and y, it's going to look like that. It's going to be stretched out some, but that's where it's going to look, and I'm going to have asymptotes along the x-axis and y-axis, because y can never be 0 and x can never be 0. So we'll work on doing some graphs here in a minute. And what is y when x is 2? Well, let's take this model that we just came up with, and we have y equals 56 over x, and then they tell me that x is 2. Y equals 56 divided by 2, which is going to be 28. Y equals 28 when x is 2. There you have it. First part of inverse variation. Okay, so modeling with inverse variation, it says, after a storm, your math class volunteers to remove debris from your yards. The table shows the time t and in minutes, and it takes a group of n students to remove the debris from an average size yard. So it talks about inverse variation, and I said inverse variation is some constant, so as one goes up, the other goes down. So as y increases, x is going to decrease, or in this case, as n increases, my minutes will decrease. It makes sense that the more students I use, the faster it's going to get cleaned up, so we won't use as much time. Therefore, the fewer students that I use, of course, it's going to take a longer amount of time. So that's your inverse variation. But let's see here. So if we're using inverse variation, we know that it is the values of x times y is going to equal k. So I have 1 times 25, 225 is going to be 225. So 1 times 225. I also have 3 times 75, which is going to give me 225, and 5 times 45 is going to give me 225. And then, of course, these two, I think it's going to give me 224, but very close to 225. So looks like k is going to be 225. So what models the time needed to clear the debris? Well, y equals k over x, and we know in this case n is going to be x, t is going to be my y. So I have t equals something over n, and then of course we said that k is going to be 225. So there you go. You got t equals 225 over n, and this says how many students should there be for the debris of an average sized yard to take 25 minutes? Well, it looks like here t is equal to 25. So we have 25 equals 225 over n. Do some cross multiplication. 25n equals 225, or n is going to equal 9. So there you have it. It should take 9 students. And that's about all I want to really discuss with inverse variation. We don't need to worry about combined this. We may have multiple variations, but oh well, combined is okay. Jointly, we're not going to get into those, so we'll do some more on our classwork.